Okay, hi everyone. My name is Ben London, and I am a real human being. This is I'm going to be presenting some work with some of my colleagues at Amazon Music. Our lead author, Alexander Buchholz, couldn't be here today, and so Malte and myself are going to do our best to present this work. This is also with Giuseppe, Benedetto, Yannik, Stein, and Thorsten, Joachims, who you heard earlier today. So Amazon Music is a streaming media platform, and if you go to the homepage of our desktop app, you'll see something like this. We have recommended content that's organized horizontally in what we call widgets, and we also have multiple widgets on the page, and we optimize the layout of the content within the widgets, and also the order of the widgets on the page, so that you hopefully have to do less scrolling to find content that you want to listen to. And both of these problems can be abstracted as ranking problems. And what I'm going to be talking about today is if you have a ranking policy and you want to know how good it is, then how can you evaluate it in a way that gives you an unbiased view of its expected utility? So typically the way that we do this is offline, using data that we've collected from an existing policy, what we call a logging policy. And the assumption that we're going to make is that this policy is randomized in some way, and typically this is just some randomization of an existing policy, like with swapping the order of items. For each record in the data set, we have some contextual features, like the user, time of day, etc. We also log the ranking that the logging policy selected, and then we log the feedback that it got on each of the items in the ranking. And so this is a semi-bandit setting where we assume that we can get feedback in the form of clicks on each item in the ranking. And then finally, we log some information about the logging policy itself. And again, what we want to do is get an unbiased estimate of this quantity, the expected number of clicks that a different policy would get if we were to put it into production. Now, just to give you an illustration of what we're talking about here, suppose this is the ranking for a specific widget, and this is the ranking that the logging policy selected, and let's assume that the user gave us 2 clicks, one on the first position, one on the fourth. Now we have a new policy that gives us a different ranking. So what would the expected number of clicks be? Well, this is inherently a counterfactual problem, because we don't know what would have happened if we had put this other policy into production. Now, there's a bunch of ways of doing this estimation, and a family of methods is inverse propensity scoring, or inverse propensity weighting. And basically, all of these estimators have the form that I'm showing here at the bottom of the slide, where we take an average over the data set, and for each record, we take a weighted sum of the clicks that we've observed for some W, which I'll define in the subsequent slides. Now, the simplest thing that we could do, the naive way, is to use vanilla IPS from the contextual bandit setting, or the top 1 setting, where we have a weight that in the denominator has the probability that the logging policy selected the entire ranking. And this is pretty straightforward, and it gives us the estimator I have here. And the nice thing about this is that we have to make minimal assumptions to get unbiased estimates. But the main downside is that the variance of this estimator is prohibitively high. It's silly, and this is because the probability that we're using in inverse propensity weighting is the probability of an entire ranking, which is very small. And to cope with this, in the ranking literature, people often make assumptions known as click models, which basically assume something about how users interact with content in a ranking. And so I'll talk about a couple of click models here. So the first one, which is pretty straightforward, is known as the item position model, which makes 2 assumptions. One is that clicks depend only on the position at which an item is ranked, and then the content of that item. The second assumption is that the clicks are independent of one another. So a click on position 1 doesn't depend on any of the other positions. And this yields a very simple importance weight where we've replaced the probability in the denominator with the marginal probability of ranking the given item at the given position. Okay, and since the marginal probability is higher than the probability of the full ranking, this reduces the variance of the estimator. By the way, one thing I haven't mentioned is that we are going to be assuming that the target policy, the policy that we want to evaluate, is deterministic, and that's why we have the indicator variable in the numerator, which basically says, did the target policy rank the same item as the logging policy at a given position? Now, the advantages of this approach are that, well, it does reduce the variance compared to the naive method, and it has very mild assumptions. And compared to the next model that I'll show you, there's no additional parameters to estimate. And if our assumptions hold about the way users interact with rankings, then we get an unbiased estimate. The problem, though, is that even though it's reduced variance, the variance is still very high. Right? And we prefer to have less variance. And that brings me to the next click model, which is actually a bit more common in practice and in literature, and that's the position-based model. So this could be viewed as kind of an extension of the item position model, where we further assume that clicks factor into a product of relevance and examination probability. And the relevance is going to be independent of the position, and the examination probability is independent of the item that's shown at that position. And so this technique uses what we call a position bias curve, which is basically a list of examination probabilities representing how likely a user is to look at any given position, independent of what's shown there. And the importance weight is just a ratio of the position biases under the target policy in the numerator and the logging policy in the denominator. And just visually, this is what's going on. So here is an example position bias curve where, naturally, the position bias decays as a function of position because people are more likely to look at the head of a ranking than the tail. And suppose that the logging policy got a click on the first position, but then the target policy ranks that item further down in the ranking. So in this case, we would actually downweight that click in the estimator because because the target policy is ranking this item further down in the ranking, whereas if the target policy ranked an item higher than it was shown by the logging policy and that item got a click, then we should upweight that click. So that's kind of intuitively what this model is doing. So given the position bias model assumptions, we get this importance weight and the corresponding estimator. So the advantage is that this greatly reduces the variance in practice. And again, if the assumptions of the click model hold, then we get an unbiased estimate. However, to use this, we need to get the position biases from somewhere, and usually those are estimated from data. And secondly, if our assumptions don't hold, or if we have incorrectly estimated the position bias, then we introduce bias. And in practice, this tends to be more biased than the item position model. So summarizing this, we have these two click models that kind of represent opposite ends of a spectrum of bias and variance trade-offs. So at one end, we have the PBM, which is high bias but low variance. And then at the other end, we have the IPM, which is low bias but high variance. And so the question that we ask is, well, can we get the best of both worlds and combine these click models? And at this point, I'm going to hand it over to Malte.
Thanks, Ben. And so for this, let's quickly revisit again like the position bias model and sort of again like what really matters here is like the ratio of these two position biases, right? So if you want to, again, if he ranks like an item that was previously ranked in position 1 and you rank it down to 20, then we need to have this ratio of position biases. Now, because as Ben said, like we have to estimate this from data, there will be probably some errors. Now, what we observed in like previous, like before we started this project, often is like sort of that it's much more difficult to do this like 1 to 20 estimation than sort of like estimating what would be the difference if we rank something from like 3 and then in a new policy it's like in position 4. And sort of, yeah, which sort of makes sense, right? Because this appears way less often in the data that we get to see to estimate these position biases. And so this observation, we can use it now as a modeling assumption, and that's what we're doing by sort of creating a new model that sort of has, again, the main assumption is that we only use the position bias model in an area close to where the item was ranked in the logging ranking, right? And which is sort of based on this observation. And to do this, we create what we call window systems, and this is really just like sort of defining for every position in the logging ranking, like for which other positions in the target ranking, we will apply the position bias model. And usually this will be somewhat close to the logging position, because that's what we've seen in the logging in the data that we collected. And so this window system in the paper is written much more generally. Like here for the purpose of the talk and the experiments, we will focus on on a particular instance of this window system, which we call banded window system, and which is really easy, simple in the sense that we will just symmetrically look around that logging position and now sort of consider the position bias model only if that sort of action here, for example, would be then ranked in one of the first 3 positions. And we do this for all the things, and so this is basically this is sort of then the window system. We also introduce for this particular window system, we introduce like a hyperparameter called the window size, which just says like how far do we go. And this is now a new hyperparameter that we have to optimize. And what we see here, if we increase the window size, then almost by definition, right, like sort of if we go large enough, then this generalizes. We find again like the PBM, because by definition this is the region where we apply the PBM. On the other hand, if we have like a window size of 0 and we just look at that at the same action, then we sort of recover the IPM. Now more formally, how this looks like is that, so again we have like a new weight now, right, for this general IPS as the OPE like formula. And as you see there's like an IPM part that looks a bit like the IPM estimator, but it also has like in this case like this window size in there, and there's the position bias part. And now it's quite easy to see once you write it down. Basically, if you have again like a big window size, we will recover like the position bias estimate, because like the left part here will be just 1/1 basically, and if we have t equals 0, so no window size, then basically the right part will also only be active, and like it will be the same ranks, because like this entire ratio, like the indicator here, will only be active if the ranks coincide. And then, but if the ranks coincide, then the position bias ratio is 1. And so that's how we recover basically the 2 extremes. And well, now we've got like a way of parameterizing this bias variance trade-off and interpolating between these 2 methods. We call the method interpol. But the downside is we need to choose a hyperparameter, another one. Now we have some theoretical results. I won't go into too much detail, but basically what they're saying are like that if in the world where we were before, like under a correctly specified position bias model, by doing sort of this mixing, we will not really lose anything, like it still stays unbiased. Again, the assumptions are strong, but they're also already strong for PBM. It just says like we are not messing up anything, basically. And this is sort of an illustration of synthetic data on what's going on, just for as a sanity check, basically. As we increase the window size, so here's like the true reward is 2.0, and we have our interpol estimator, and we increase the window size, and you see that like going from window size 0, so the IPM, we have high variance but low bias, and then if we increase the window size, we come to a position where the estimate gets biased, but like lower variance. This is a very similar figure, like saying basically the same thing, but also having like a mean square error curve in there. And for this particular example, it's just for illustration again, like we see that the minimum mean square error is found like not at the extremes, right? And that's what we then saw a lot in the experiments, basically. In the interest of time, I'll make this very quick. So we have more synthetic experiments. We also have some real data experiments on Amazon music ranking data close to what Ben introduced. And basically what I want you to focus on here again is, so lower is better, mean square error. it's not so obvious because they're quite close to zero, but like often, again, like the lowest mean square error is like achieved for intermediary sort of window sizes, so not in extremes, indicating that we can get there something out of that. Then finally, before concluding, so we also applied this to learning, right? So where the idea is if we have like a better estimator or policy estimator, then we can also use that as a training objective. And again, I in the interest of time, like the message here is again like, so DCG now higher is better, that for most of these curves, one curve represents like one experiment, meaning different, this is synthetic, but like different conditions on like the logging policy, the randomization, how well we could estimate the position bias. And again, the message here is like that now, usually the maximum of one of these curves, again, one curve is one experiment, is not at the extremes, unless like we have perfect conditions, say we have the perfect position bias curve, or we have like a highly randomized logging policy, which is not always very realistic. Finally, like again, like we only talked about this banded window system, but I think the beauty of this is, and there's more about this in the paper, is that we can really specify this window system arbitrarily. And so this banded window system is sort of, it's very close to the normal position bias thing, right? And you can think of it like, if you have a user interface that sort of scrolls smoothly, then this seems to make sense. But some user interfaces are, for example, carousels that swap all at the sudden, right? Like you scroll and then you have 7 new items, not one by one, but a completely new thing. If you imply that, like, and you could build like a window system that accounts for that, basically. Because like just saying, now estimating like position from this first slate to the second slate with the old model, with the normal position bias model might be very difficult to estimate. So to conclude, I think that there's evidence that we can sometimes like find a better bias variance trade-off. Again, like these window systems can be defined arbitrarily, and I think that there's a lot of room for future work in exploring those for different user interfaces, especially now that they're becoming crazy, right? Like this old grid layout might be a bit outdated someday. More theoretical NMTs, more experiments. We also have a different version of the estimator for the limited visibility setting, meaning that for now and for this talk, we assume that like we always see the entire ranking, but sometimes you only want to rank k out of a lot, and then you have different biases and so on. So we can account for that as well. And well, the big caveat, and what also needs more work, is like choosing this hyperparameter, right, for the banded window system. And what we did basically in like until now is using these methods called slope or slope plus, and empirically that worked kind of well, but like they actually make assumptions, these methods that are not satisfied by the interpol estimator. So yeah, that could also be some future work in finding some better methods there. With that, thank you very much. I hope you have some questions.